Okay, so you remember I mentioned to you that I mean there are different types of singularities. We discussed singularities of the type of a pole types, some nth order pole. But so if I look at the pole, nth order pole, say at z naught, then the Laurent expansion will start from 1 over z minus z naught to the power of n, right? Some coefficient, some, let's call it d minus n plus the lower ones. And so on. The worst singularity is this one, right? That's what it means to say nth order pole. Okay? But notice that all of these things, they are single valued. So if suppose z naught is here and I take z here and move around, right? Go around in a circle and come back, it will come back to its original value. Because after all, what is this object? This is in the polar coordinate. If I take this to be the r, I mean choose the z naught as origin, okay? Then if you take this r and this angle is theta, then this z is simply, I mean z minus z0 is simply r times e to the I theta, yes, and then this thing simply becomes d minus n divided by r to the n times e to the I n theta, and then similarly all the lower terms. But the point here is that as theta goes to theta goes from 0 to 2 pi, it comes back to its original value, right? So it's single valued. It has singularity at z naught, but if you are away from z naught and you move around, it's single valued, right? But now we also talked about other types of singularities, which are the multi-valued, where functions are multi-valued, right? So for example, multi-valued functions. So for example, let's take z to the power of half. Okay, this is an example of multi-valued function, because again, if you go to the polar coordinates, right, again z is equal to r times, or z minus, let me call it z minus z naught to the power of half. Okay, then if you write z minus z naught equal to r times e to the I theta, then this is the same as r to the half times e to the I theta by 2, right? And now if you take theta, you shift theta to theta plus 2 pi, the answer is not the same, right? Because under this you get r to the half e to the power of I theta plus 2 pi by 2, which is the same as minus r to the half e to the I theta by 2, because this 2 cancels from this, so you get e to the I pi, and e to the I pi is minus 1, right? So you get that. So it's not single valued. So if you now go around z naught, you go around, you come back, you do not come back to its original value, but it's minus the original value, right? So there is an example of multi-valued function, right? Okay. So now what we can say about this multi-valued functions? I mean, so what does it mean? So again, let me go back to, so let's continue with this example. So if I see now I look at this, I mean, if I take any point here and consider not a path which goes around z naught, but consider a path going like this. So it is not going around z naught. Okay, in this case, the function will come back to its original value, right? Because what's going to happen? So theta starts from, say, some value. As you go around here, theta increases to some maximum value, and then as you go around here, it comes back to 0 again. It doesn't become 2 pi, you see. So for such a path, it will come back to its original value, right? So the point is that any path, you take any closed path and you come back to the same point, if that path does not encircle z naught, then it comes back to its original value, right? Only problem is considering those paths which encircle z naught. That's only time when the function doesn't come back to its original value. Okay. So so this point, so I mean any other path, you see, any other path would be fine. It will come back to its original value, or any path like that will come back to its original value. Only thing is only a path which, so if you choose z naught here, choose say z here, any path which goes around z0, that will not come back to its original value, because now you see theta is increasing all the way and coming back to theta plus 2 pi, right? Whereas if you choose a path like this, which just, I mean, doesn't encircle z0, it's a little bit above, then theta increases, but then as you go around here, it decreases again and comes back to its original value, right? So such a point around which, I mean, so the point z0 is called the branch point. So any path which goes around the branch point, then the function doesn't come back to its original value. But if it doesn't go around the branch point, it comes back to its original value, right? So z0 is called, this is called the branch point. Okay. Okay. So now what we can do, I mean, all these theorems that we have used, I mean, all the residue theorems, Cauchy theorem, everything was proven for single valued functions, right? So the question is, can we do something for in this situation so that we are still able to use the Cauchy theorem, etc., right? I mean, all those theorems that we have studied so far, can we still use it? I mean, do something. Of course, you have to modify something, right? But what is the way to go about it? So the idea is the following. Yeah, because of this, precisely this fact that the single valuedness breaks down only for the paths which go around z0, right? So what you do, so you start from z0, and so here is my full complex plane, and draw a line which goes from z0 to infinity. I should also mention that any path which goes around infinity also is not single valued. And this is where you see I skipped one chapter, one section, which is called conformal transformation. I skipped that. There we but let me just at least summarize some important point here. I mean, I will not go into details about conformal transformation now, but I will just say a few things. So in the complex plane, okay, is the set of all points where modulus of z is finite, no matter how large, but it's finite, right? Infinity is not part of it, right? But you can add a point at infinity, one point at infinity, okay? So how do you do that? The way to do that is what is called stereographic projection. Stereographic projection. Okay, and the idea is the following. Suppose I take a two sphere. This is a two sphere. Okay, this is a two-dimensional sphere, and put it on a plane. So the south pole, let's call it the south pole, and let's call that north pole of the sphere. So this point, you put this this point exactly just touches this plane. Okay, so this is a two-dimensional plane. Okay, which means a complex. I mean, in two-dimensional flat plane, you can always introduce complex coordinate x plus iy equal to z. So what I've done is I have this plane here, and I put the ball on top of it. Okay, the point which is touching this plane, I call that south pole, and the point antipodal point I call north pole. Okay. Now what we can do is that we can map the points on the two sphere to the plane, okay, by the following way. Choose any point here. So what do I mean by saying map? That for every point I should associate a point here, right? And it will be one-to-one association. Okay. So the way to do it is you draw a line starting from the north pole, passing through this point, okay, and then continue is going to intersect somewhere, right? So wherever it intersects, you declare that this point is mapped to that point. Okay, this is clearly one-to-one, except for the north pole. So forget the north pole, but any other point on the sphere, I mean, this rule gives you a unique associates to that point a unique point on the plane, right? So you can think of this complex plane as just a two sphere, but without the point at the north pole. Without the point at north pole, because if you try to use this rule to figure out where this north pole is mapped to, well, north pole is mapped to infinity, right? Because you can see if you take a circle here, I mean, you know, the azimuthal circle, then that is going to be mapped by this rule to a circle on the plane, with this being the origin, right? But as you start going closer and closer, I mean, so closer and closer, these lines are going to become, I mean, farther and farther away, right? So the North Pole is really the limit where this circle, I mean, the circle in the plane, you take the radius to infinity, right? That is where the North Pole will be. Okay. So if you, when the statement that people, I mean, you'll hear this statement many times, complex plane plus a point at infinity is topologically the same as a two sphere. Okay, this is a statement. That is the meaning of that statement, because what we are doing is that for the entire this infinite circle, we are just associating one point here. North Pole is just one point, right? So all this doesn't matter in which direction you go to infinity, right? All that is identified with just one point, North Pole here. Okay, so you're only adding one point at infinity. Okay, so the complex plane plus a point at infinity is topologically, is called topologically a two sphere, a two-dimensional sphere. I mean, two sphere meaning two-dimensional sphere. Okay, so this is one thing. So somehow what we'll always do, think about is we'll take this complex plane but also add a point at infinity. Okay, but now you can ask the question, I mean, okay, fine, I point at infinity, but how will I try to understand the properties of various functions at that point at infinity, right? So to do that, the most convenient thing to do is to make a coordinate transformation. So do a coordinate transformation. So just a simple coordinate transformation, z equal to 1 over z prime. This is what the inversion, no? 1 over z prime. So what will that do? The point at infinity in the z plane, so let's draw the map. So I have here is a z plane, okay, which means that here the points are coordinatized by z, and here is my z prime plane. Okay, so here the coordinates are labeled by z prime. So if you make this transformation, so let's say a point here which has some radius r times e to the I theta, I mean the distance in the polar coordinate is that, well, so z prime is 1 over z. I mean, this relation also implies, of course, z prime is 1 over z, right? So z prime will become 1 over r times e to the I theta, which means if you take e to the I theta up, it becomes e to the minus I theta. So it will be mapped to, if this is theta, so minus theta will be somewhere here, okay, and r, I mean, and the modulus of that will become 1 over r, right? So it will be some point here, right? So this length will be 1 over r, and this angle is minus theta. I mean, so minus meaning down. Okay, so this point is mapped there. Now it's clear that as r goes to infinity, okay, this 1 over r becomes smaller and smaller, and it will come to the origin, right? And notice that it indeed, I mean, whether you go, it doesn't matter then the value of theta, right? No matter what value of theta you choose, it's all going to be mapped there, right? Okay, so you do this map, and then you study in the z. So I'm given some function of z here, right? So you do this map. So what does it mean? So the function, the value of this function at this point will be the same as the value of the function at that point, right? And so on. So you do this map, and then you can study. So so function of z will be mapped to some function of z prime. Let's call it f prime z prime, where what is f prime z prime? It is simply f of 1 over z, right? So you do this, and then you just study what is its behavior around z prime equal to 0, because z prime equal to 0 is the point at infinity here, right? So if you want to, for example, ask the question whether the function is multi-valued around infinity here, that is the same question you ask here, if whether the function in the z prime plane is multi-valued around z prime equal to 0, right? So indeed, once you accept this, I mean, okay, so this is the, yeah. Okay, since I'm not going to discuss too much about conformal transformation, but let me just make one statement that Suppose you want to ask the following question. I have a sphere, I mean as I said this plane with a point at infinity is a 2 sphere, right. Now I want to make some coordinate transformation, not just this, I mean this is just a special example, but in general I make some coordinate transformation. Okay. So z prime will be some function of z, I mean not this function, I mean some function, z prime will be some function of z. But I am going to make analytic transformations, I mean they will not depend on z bar. Okay. So I will only make, in other words z prime will be an analytic function. Okay. So I mean okay, more or less it may have poles, but does not matter, but it will not be, I mean there may be some isolated singularities that may be okay, but it will be analytic everywhere else. The singularity of the pole type, not the square root types and so on. Okay. So if I do this then but I want to do the following way. I want to have this map a one-to-one map, not, you know, I mean this function will give you, for every z it will give you some complex number, right, that is what it will do, but I want it to be one-to-one. Okay. So the point here is that what I want to do is that I have this z plane and z prime plane, a point here, I mean a point will be mapped to some point, right, but one-to-one means that another point should also not be mapped to the same point here, it should be one-to-one map. Okay. But I will also include the point at infinity here in this plane, so infinity is included here as well as infinity is included here. Okay. So I want to do that. So infinity on this plane should be mapped to one point here, perhaps even infinity maybe, or maybe some finite point, and similarly some point here should be mapped to the infinity here. Okay. If you demand that, then the most general function transformation is actually what is called rational functions, rational linear functions, or the following type: az plus b divided by cz plus d. This is the most general transformation. Okay, this is called conformal transformation. I mean, well, I mean in some sense, actually conformal transformation is much more general. Conformal transformation is for arbitrary function. But if you further restrict yourself to this requiring that it is a one-to-one map, then that becomes that. This is very useful because this is a map from a 2 sphere to 2 sphere, because after all complex plane infinity plus infinity is a 2 sphere, this is also a 2 sphere, right. So this, since it is a one-to-one map, we are saying is a one-to-one map from a 2 sphere to 2 sphere, right. That is what the thing. And indeed you can see that this is a one-to-one map, because let us invert it. I mean surely for every given z there will be some well defined z prime from this formula, right. But the question is, for one-to-one statement is that for given z prime is z also unique, that is the question, right. So I want to invert this relation, and that you can do is immediately just multiply this on the other side. So you get here cz plus d times z prime equal to az plus b, and then solve for z. So combine, put the together that, so cz prime minus a times z, right, and then this is equal to b minus dz prime, right. So z therefore is b minus dz prime divided by cz prime minus a. So it's again is a unique, right. If given a z prime, it gives you a unique z, right. Furthermore, if you look at how the things are mapped, so if you the point z equal to minus d by c, you look at the z equal to minus d divided by c. Well, I forgot to mention a, b, c, d are some complex numbers. Okay. So, but with the determinant not equal to 1. So a d not equal to 0. A d minus b c should not be equal to 0. The reason is if this was 0. So the determinant, if you look at a, b, c, d, the determinant of this must not be 0, right? Because you remember that if determinant is 0, then these two rows are linearly dependent on each other. That means c, d must be a multiple of a, b, right? But then this whole thing just cancels out and becomes a constant. So z prime becomes a constant. So that is not a meaningful map, no. So we need to have determinant not equal to 0. But otherwise a, b, c, d are arbitrary complex numbers. So z equal to minus d divided by c is again a complex number. It will be some point, whatever, depending on the value of d and c, right. That point is mapped to infinity here, because you see this becomes 0, so z prime is infinity. So that point is mapped there, and vice versa. If you look at which point in z prime plane is mapped to infinity, you can see z prime equal to a divided by c, right? Whatever the a divided by c is, that's mapped to the infinity there. Okay. So this is we will use this later in the 4th chapter when we discuss hypergeometric differential equations. Okay. These kinds of transformations play a very important role in physics of string theory. Okay, I mean string theory is something which appears in the as a theory of gravity. Okay, so in string theory this plays a very important role. Okay. But I mean I will see how it goes. If there is more time, I will come back to it. But for the time being, I think this is enough for you to know, to follow the rest of the things. All right. So now let's go back to our the square root of z minus z naught. This function f of z, which was square root of z minus z naught to the half, right? We said, of course, z naught is a branch point, but also z prime. Z equal to infinity is also a branch point. To see that, as I said, you have to make a coordinate transformation to study what is its behavior near infinity, right? So what is if I write z goes to 1 over z, so that means 1 over z prime minus z naught. So this is the same as that in the coordinate z prime coordinate, because z is 1 over z prime, right? To the power of half, which is 1 over z prime. You take out as a common factor, so you get 1 over z prime to the half, and 1 minus z naught z prime to the half. And then we said z prime equal to 0 is the infinity here, right? Now look at the z prime around 0. Z prime around 0, it's obviously multi-valued because there's a square root there, right? If you write z prime equal to some r prime, where r prime is small, or okay, so take some small value, e to the I theta prime, then you see this part becomes 1 over square root of r prime times e to the I theta prime by 2. And then if you take theta prime to 0, theta prime plus 2 pi, you come back with a minus sign, right? So that shows that infinity is also a branch point. Okay. Fine. So what is the way to? So now let me go back to the thing about how we can kind of slightly modify the whole situation so that we can still use all the theorems that we have, Cauchy theorem, residue theorem, everything we can use. So the way to picture this is the following. So here is my point z naught, and infinity. Okay, infinity doesn't matter which direction you choose, because as I said, infinity is just one point. So for convenience, let me just choose along the real axis, although it doesn't have to be. It can be any direction. Okay. All right. So what we will do is so I have this complex plane, and I will just cut this complex plane, right? With the scissors, I say, for example, cut it all the way up to z naught, Okay. Now, so you take, so this is now cut. You see, it's not. So there is no path which goes around and comes back here, because it's cut now, right? So what? But of course, you want to have something closed somehow. You cannot have. You don't want to have some boundaries like that. That's not very useful. So what you do, as you come back here, because the function becomes a minus, right? You get, for this function, say this function here, when you rotate, when you go around this thing, then f becomes minus f, right? It's gone. So of course you cannot. The reason why we cut is that because if I come here, then it is no longer multi-valued, no longer single-valued, right? So I cut it, right? And then when I further move theta to theta plus 2 over 2 pi, right? Then we attach another sheet here, another sheet. We say that, okay, after this it doesn't go back to the original sheet, but it goes to another sheet. Okay, so like you attach 2 sheets. Okay, so after that it goes. So this is my first sheet. Then I have a second sheet, which is again of this type, second sheet, where it starts from z naught and again infinity. Here also it's cut. Okay, so what I do, I go in the first sheet like this here, come here, but then I enter the second sheet, the upper part of the second sheet, then come back here. But now you see 2 times when I rotate, f comes back to its original value, right. So then I can go back to this sheet here, right. So this is the way to picture. So it's very difficult to draw it, but it's like you have cut this, you have cut this. Let's call this the upper part, and that's the lower part of this cut. This is the upper part and the lower part of the cut, right. Then what you do, the lower part of this cut, this first sheet, you glue to the upper part of the second sheet, okay. And then you come back here, then the lower part of this second sheet is glued to the upper part of the first sheet, okay. Now in this big space, this function is completely single valued, right. So then you can use all your theorems, whatever you have learned, right. So this is the idea. For a multi-valued function, you have this idea of putting sheets together, right. And okay, in this case I just needed 2 sheets because it was a square root, right. Suppose it was a 1 over n. Suppose this was 1 over n. Okay, then you will need n sheets, because when you take so again write z minus z0 equal to r e to the I theta, and so if you take theta goes to theta plus 2 pi, then this comes back with a phase. So f goes to f times e to the power of 2 pi I over n, right. Let me just substitute this. This is r e to the I theta, so this is the same as r to the 1 over n e to the I theta divided by n. So when you shift theta to theta plus 2 pi, f will pick up this phase, e to the 2 pi I over n. So you need to go n times around to come back to its original value, right. So you will need to put n sheets, right, and it will be successive. So from the lower boundary of the first sheet will be glued to the upper boundary of the second sheet, lower boundary of the second sheet will be glued to the upper boundary of the third sheet, and so on. You keep going until the last sheet, lower boundary of the last sheet is glued to the upper boundary of the first sheet. Okay. And on this big space, everything is, such functions are single valued. So depending on what kind of function you are given, you have to choose the appropriate branch cover. This is called branch covering, right. You have to choose a suitable branch covering such that the function becomes single valued. Okay. Sometimes you may need to use infinite number of sheets, right. An example of that is the log function. So if you take log function, log of z, let's say. Okay. Now again, let's write. Okay, let me put z minus z naught again. If you again write z minus z naught as that, this is the same as log r times e to the I theta. But log of the product of two things is the sum of the logs, right? So it's log of r plus log of e to the I theta, which is the same as log of r plus I theta, right? Log of e to the I theta is I theta. So now you see theta goes to theta plus 2 pi, this keeps additive, and it will never come back to its original value, no matter how many times you rotate, right? So in this case, you need to put infinite number of sheets, so that log would become single valued, because it never comes back to its original value. So infinite number of sheets you have to stack. Okay, at this stage it may not look okay. So what? You may say, so what, right? Okay, you can do that, but we will see how we can use it for actually computing some things. Another example also which is discussed here, so let me write it down. So consider a function which is something like this, f equal to let's say z square minus 1 to the half. So now you see this has so this is of course z minus 1 to the half times z plus 1 to the half, right? Because z square minus 1 is z minus 1 times z plus 1. So it's clear from here that there is a branch point at z equal to 1 and a branch point at z equal to minus 1, right? So if you draw the plane, so at plus 1 and minus 1, this function has a branch point. And the easiest way to see it is the following. Suppose z is some point here. Let's draw these two lines here, joining from +1 to z and -1 to z. Let's use a polar coordinate for this one. So let's call it r plus e to the I theta plus, and this one let's call it this thing is r minus times e to the I theta minus. That's just I mean, given these 2 points, given this point, of course you can determine what is r minus. This r minus is the length, and theta minus is this angle. Here r plus is this length and theta plus is this angle. Okay. So then what is this? This becomes in this variables, this simply becomes square root of r minus times r plus, and then e to the power of I theta minus plus theta plus divided by 2, right? I mean, yeah, just substitute this. I mean, what this means is that z minus 1 is r plus e to the I theta plus, and z plus 1 is r minus e to the I theta minus. Let's substitute that. Okay. Now, suppose I take a path, I move the z around and just in a path which only goes around one of the branch points, say +1. Then in this process, theta plus will shift to theta plus 2 pi, but theta minus will not shift, because theta minus, okay, this angle theta minus this decreases and again increases and comes back to its original value, right? So inside around such a path, theta minus remains the same, but theta plus shifts by 2 pi, but 2 pi divided by 2 is pi, so you get e to the I pi, so you get a minus sign. So when you move around such a path, it picks up a minus sign, so it's not single valued. Same way, if you choose a path which is like this, which goes around just this singularity, this point, -1. Once again, this time theta minus picks up shifts by 2 pi, but theta plus doesn't shift. So again, you get a minus sign, right? Of course, if you choose some path which doesn't go around either of them, then both the value theta minus and theta plus come back to its original value, so nothing happens. It's single valued then, right? So the branch points are these two. Okay. Now, what about if you take a path which encircles both? Suppose you choose a path like this. Okay. In this case, both theta plus and theta minus shift by 2 pi, right? So this becomes the total shift is 4 pi, and 4 pi divided by 2 is 2 pi. So there's no phase. E to the I 2 pi I is 1, so it comes back to its original value, right? So in fact, this also tells you that at infinity there cannot be any branch point, because I mean this. I mean, after all, remember this you can take it as large as you wish. I mean, these paths you can choose as large as you wish, right? Larger and larger circle. And in the stereographic projection, it was like this, right? This large circle is an azimuthal circle around the North Pole, right? So since the function is coming back to its original value for large circles, so going around here also it comes back to its original value. So going around the North Pole doesn't change the function, right? But North Pole is a point at infinity, right? That's a quick way of seeing it. Otherwise, if you are not convinced with that, just then go to the coordinate z prime, z equal to 1 over z prime, and then you will see that indeed it's true, that at point at infinity there is no branch. I mean, it's single valued if you go around infinity, right? So the only branch points are this and that. So in this case, what you can do, you can choose your branch cut here. You just cut your complex plane here, put another sheet. You need only 2 sheets, because if you go around twice, you come back to its original value, right? Because of square root. Okay. So you cut this and put another sheet. Once again, you do the same thing. You have upper and lower boundaries of each of this sheet. Lower one will be connected to the upper one of the other one, and lower one of that will be connected to upper one of this. And there its function becomes single valued. This is quite remarkable, actually. I mean, this is just one of the simplest possible situations, but you can start considering even more complicated situations where where you can let's see, where you have so branch points like this. So just give you one example, branch points like this with the cut being here. Okay. So this would be a situation where, let's say, I don't know, 0, 1, Z1, Z2, right? I mean, you can choose arbitrary points, Z1, Z2, Z3, Z4. You have 4 branch points. Okay. So for example, a function of this type, Z minus Z1, Z minus Z2, Z minus Z3, and Z minus Z4, square root of that, for example. If you choose a function like this, okay, this function will have 4 branch points, Z1, Z2, Z3, and Z4. It's a square root again, so you need only 2 sheets again. This one, so and you can just choose a cut, I mean, between any pair of points. So this pair and that point, I just chose this. It doesn't have to be that. You could have chosen a cut connecting Z1 and Z4 and the other cut between Z2 and Z3. But just to, just choose, pick one of them, pick one choice. So I have cut the surface here, and I've cut the surface here. Now you see in this part, it's all single valued, because if I choose a path here, it's single valued because it's going around both of these guys, right? For that argument works. So inside here, it's all single valued. The only problem is it would, if I had gone like that, it would not. But anyway, I've cut it, so I cannot go, right? In order to go, I have to go to the second sheet, and then again come back. Now, so you can ask the question. By the way, the surface that you get by this kinds of attaching the sheets is called Riemann surface. It's called Riemann surface. Okay. Now, this Riemann surface that you get is it'll be hard to imagine that, but is topologically a surface of a donut. If you take a ring, like this, how to draw it? You know what I mean? Take a cylinder and join the 2 ends, no? So it becomes a ring. No? Surface of the ring is, of course, 2-dimensional. Okay? And the claim is that this Riemann surface that you get by gluing the 2 sheets is topologically the same as that. Okay. Huh? It's topologically a torus. Well, it's a torus. Huh? It's a torus. You can do more. Suppose I put one more. 4 of them, 6 of them. Z minus Z5, Z minus Z6. Okay. So here is my Z5 and Z6. Again, I can choose 3 branch cuts, okay, and join 2 sheets. And the surface that you get is topologically the same as this surface. What do I mean? I mean, cut out 2 holes here, and attach a tube. Okay. So that a lot of fun things are there in this whole thing. Yeah, right. So you join like this. Join a tube here on these 2 holes. And in general, the more you can keep increasing the cuts, the more you introduce the cuts. It's like just joining more and more tubes. This is the way it works. Okay, one way to see that, maybe one way to see this is the following. Already for this, or the simplest case here. The simplest case. See, in the torus, this is a torus. This is called a torus, two-dimensional torus. Here, you see, if you take a path like this cannot be contracted to a point. When we discuss simply connected spaces or non-simply connected spaces, this space is not simply connected, right? If you take a closed path like that, this on the surface, you can shrink it to a point without leaving the surface. The curve always stays in the surface, and you can shrink it to a point. But if you take a curve which is going around this one of the thing, then there is no way you can shrink it to a point. While the curve stays on the surface, right? And also without breaking the ring. You're not allowed to break the ring. Huh? Okay. So you cannot shrink it. Same way, if you take a closed curve like that, this also cannot be shrunk to a point. So there are two independent curves which cannot be shrunk to a point on the torus. Okay. I mean, any other closed curve can be obtained by taking combinations of this. Okay. So these are called two generators, which generate all the non-shrinkable curves here. Now, if you look here, if you take a path like this, you see here it's single valued. We saw single valued, but there is no way I can shrink it to a point, right? In order to shrink to a point, it has to pass through this cut, but it's not possible, right? I mean, it's not possible. You cannot do that. What about this curve? Well, this curve is not different from that, right? Why? Because say I make this curve longer and longer and longer, so it goes to infinity, but infinity is the north pole. Nothing happens to the north pole. You can move it back, and so that curve can be continuously deformed to this curve. So this is not different from that. Okay. So this curve, for example, let's say gives you that, say is mapped to that curve, closed curve. Then you can have another curve which is also closed but which cannot be shrunk. It's the following. You go from the upper part of this here, go to the next sheet, and in the next sheet you come back here and you come back there again. That's again another closed curve which is not shrinkable to a point. Okay. And so that will be this one. So there are only these two independent things. Everything else can be obtained by combinations of this. Right? This is one way of seeing that topologically they are the same. I mean, it's clear that now if you start putting more and more, I mean, now if you put one more here, then there is another two independent curves, which are, so here this is these two independent curves here. And then similarly, by going through all such possibilities, you can also generate these two. Okay. So this is the way you see that topologically is the same. These things play a very important role in doing string perturbation theory. You know, string theory is like, I mean, if you take a closed string theory, you know, you have not done quantum field theory, but in quantum field theory, what you will do is that you develop a perturbation series, okay, and there are various Feynman diagrams which you have to. I mean, probably you don't know anything about it; these are just words. Huh? But okay, there are several diagrams which you have to. So even for not the string theory, ordinary field theory, you have to suppose I'm looking at scattering of some particles, say 4 particles scattering, 2 particles coming in and 2 particles going out. Then there are all possible diagrams you have to consider. For example, this diagram, or I mean, the simplest diagram is, for example, this, right? Another diagram could be where some particle is going virtually, and so these 2 particles join. And they give 2 particles which come back again and give you this particle. So this kinds of all possible, or you can do even more complicated like that. No? So these are called loops. You have to sum over loops to get the full answer. Okay. In the context of string, this particle will be replaced by a string moving. Right. Similarly, here this will be like that. This will be like that. Right. Now here, if you look at this here, this is all fine. But now look at the particle which is going in the. These are called intermediate particles, because this is not what is coming out. So the intermediate part will be replaced by string. So what do you get? You get that space, right? Here again, here you get this space, this and so on. So these are what this appears in the string loop expansion. Okay. So actually, all these play an important role. Sorry, there was a digression here. Now, let me come back to. So these are very interesting things. I mean, of course, you see, I mean, this whole theory developed, you know, starting from this just a simple observation to make something single valued, right? You enlarge the space, and then there's a whole new mathematics started from there, you know, where complete classification of all these geometries was introduced. Okay. Now, so now let me work out a particular to show how this can be useful. So I will do this integral, and this integral will also will appear later in this chapter. So I will try to work out Okay. So suppose I want to compute this integral, which is so let me call this integral 0 to infinity x to the p minus 1 divided by x square plus 1 dx, where p is greater than, strictly greater than 0, p is some real, and strictly greater than 0 and strictly less than 2. So this is the range. So this is what we want to integrate. Now why this range? You can understand in the following way. I mean, this function, this function is perfectly fine, right? I mean, anywhere between 0 and infinity, except possibly the problem could happen at 0 or infinity, right? Now near the 0, near x equal to 0, you can forget this x square. X square is very small compared to 1, right? So this integral, so near 0 is simply x to the p minus 1 dx integral, right? Near 0. If I'm just integrating the small region near 0, I can ignore that. But that integral is simply x to the p divided by x to the p divided by p. Or another way to say is that, you see, if p is 0, suppose p was equal to 0, not suppose I didn't have this strictly greater than 0. If p was equal to 0, this would be 1 over x, and dx divided by x is singular because the logarithm of x, and x goes to 0, it becomes infinity. Log of 0 is infinity, right? I mean minus infinity, but it blows up. So that's why, and of course for p negative it's even worse, right? If you take p to be even negative numbers, this will become only worse and worse singularity, right? So that's why this p greater than 0 is to make sure that at the 0 the integral doesn't blow up. Similarly, if you look at x going to infinity limit, x going to near infinity, you see I can forget this 1, right? Because x square is much larger than 1. So in that case the integral becomes x to the power of p plus 1 dx, right? So p minus 1, sorry, p minus 3, p minus 1 minus 2 minus 3, right? So this is the same as x to the power of p minus 2 divided by p minus 2, right? The integral. So if p was if p was equal to 2, of course this becomes logarithm, because if p was equal to 2, this becomes 1 over x, dx divided by x integral is logarithm, log of x, and x goes to infinity, log blows up. And of course for p greater than 2, this becomes even worse. It blows up even more strongly, right? So that's why the range is this. So in this range the integral is well defined. Yeah, indeed, you see that if p is less than 2, this is negative power, so this goes to 0 at infinity, right? Okay, so we want to do this integral. Actually, this this integral, although I said p is real, but in fact this can be extended to, even if p was complex, you have a condition that the real part of the p is strictly greater than 0 and strictly less than 2. But for the moment, let's just take p to be real. Okay. Okay. So what we will do? So where is so suppose I want to use some contour integral techniques and so on. So I will replace x by z, right? Okay. But if you now replace this by z, then clearly there is a branch point at z equal to 0 and at z equal to infinity, right? The branch point. So there's a branch cut between 0 and infinity. Okay. So if you replace this by z a complex variable z square plus 1, then this function has a branch point at z equal to 0. So here is my, okay, this is z equal to 0 and at infinity. So I can choose, as I said, any branch cut, but let me just conveniently choose at the origin, on the real axis. So I cut this. Yeah? So this is cut. Okay. And of course I have to put another sheet. This is actually it depends on the value of p. If p is a rational number, then you need only a finite number of sheets, right? But if p is an irrational number, you'll need infinite number of sheets, right? There's no way. It'll never come back to its original value if p is an irrational number. But anyway, we don't need to care about all that. Actually, we'll work only in one sheet finally. Finally, we'll always work in one sheet. Okay. So now, so I'll do this. So I cut this, and now let's consider a path like this. So I come down like here, go around this origin. This is a small circle, and go like that. Okay. Consider this path. This is my path C. So this picture is the following. So this path is on the upper boundary, right, of this cut. I mean this cut surface, and this path is in the lower boundary. Okay. Now choose. I mean, you have to choose. I mean, you see, once you have cut here, then the function here it's all fine. I mean, there's no problem with the function. Is everywhere here. Of course, the value here will not be the same as the value there, but who cares? Because anyway, after that, I will go to the next sheet if I want to continue. But I don't want to continue. I just want to stay here, right? So all of this path is in just one sheet. Choose any sheet that you wish and work there. Okay. So let me choose my sheet in such a way that so in this sheet, the z, when we write z as a polar coordinate r times e to the I theta, theta is between 0 and 2 pi. Between 0 and 2 pi. Okay. So I mean, this is the first. Let me call it. This is the first sheet. If you go to the second sheet, theta will be between 2 pi and 4 pi, right? And it keeps going like that. But I will be working just in the first sheet. Yeah. Answer will be, the final result will be independent of which sheet you choose. And I will leave that as an exercise for you, because it's instructive to see. You know, it doesn't matter which sheet you had chosen to evaluate this integral. Final answer will be the same. Okay. Okay. So having done this, then so let's evaluate this integral, this contour integral. So this contour integral of this function z to the p minus 1 dz z square plus 1. Okay. Idea is, of course, finally what actually let me even consider this. The contour is not just this. You take now this is not visible, right? But you draw a circle and come back here. So some radius r, where I'm going to take r to finally infinity limit. This is what we usually do, right? You take r to infinity limit in the end of the calculation. So this is my full, yeah, I mean the contour. So of course the result of this contour integral will be, I can apply residue theorem here, because inside this region the function is all well behaved, it's analytic. I mean, apart from possible poles, right? So so this will be just the sum of the residues, 2 pi I, sum of the residues at whatever the poles are. The poles you can immediately see where they are. Z equal to plus minus I. So Z, remember, no, we shouldn't say just I, because I've written Z as this, okay, and theta is between 0 and 2 pi in our sheet. If you have chosen a different sheet, okay, it will be different. But in this sheet it is this. So it means Z equal to e to the power of 1, e to the I pi by 2, e to the I pi by 2, because Z equal to I is somewhere here, right? That angle is I pi by, theta is pi by 2. So it's e to the I pi by 2. And the next one will be here, and so let's call it Z1 and Z2, e to the power of 3 I pi by 2. It's crucial to write it like this. You see, it's not, I mean, if you write it like I and minus I, of course it's true. This is true, that this is equal to I and that's equal to minus I. But the point is that eventually we'll have to take Z1 to some power which is not an integer, right? So it does matter, I mean, what you choose for the I. You see, this is equal to I, but also I can write it as e to the I 5 pi by 2. This is also I, right? But this raised to the power of p minus 1, where p is not an integer, and that raised to the p minus 1 is not the same in general. So you have to be careful. So once you have chosen if you have chosen this sheet, okay, then of course you should choose that, right? Okay. Yeah. So, okay, so in our sheet, this is what it is. These are the two positions of the poles, and so okay, of course, yeah. So there are some of the residue you can calculate what it is. These simple poles. I mean, after all, this I can write it. This is the same as z to the p minus 1 divided by z minus e to the I z minus z1 times z minus z2. I can write it like that. These are the positions of the poles. So the residue will be simply the residue at z1 will be simply multiply this by z minus z1 and take the limit z equal to z1, right? So which means, so what do you get? So let's compute residue at z1. Residue at z1 is the same as multiply this by z minus z1, so it cancels, and then the remaining part you substitute z by z1. So this becomes z1 to the p minus 1 divided by z1 minus z2, right? Which is okay. I mean, the only place where you need to be careful about it is when it's raised to something which is not an integer. This one is fine, denominator is fine, it's integer. So I don't need to worry too much about that. So this is I, that is minus I. So this becomes 2I down. But up you have e to the power of I p minus 1 pi by 2. So this is 2 pi I 1 over 2I times e to the I p minus 1 pi by 2. Yeah, this is counterclockwise, so it's fine. Okay. And then the second one at z2, you do the same thing. So at z2, what will happen? This will be just z2 to the p minus 1 and z2 minus z1, right? Because you multiply by z minus z2, so this cancels. And then for the remaining places, you just put z2. So is this. So in this case now is minus I, so it's minus 2I. And this becomes 3 e to the I p minus 1, 3 pi by 2. So this becomes minus 1 over 2I e to the 3I pi by 2 times p minus 1. Okay. So that's the result. So this result of this entire integral is that in this closed contour. No. Okay. But now let's look at let's see precisely what this is. I mean, let's try to separate them out. So this big contour C is okay. There is a part which is this infinite circle, gamma r. I mean, infinite meaning radius r circle, plus here you have 0 to r, right? 0. Okay. I mean, think of epsilon, doesn't matter. So put here epsilon. Anyway, epsilon will go to 0 in the end. So this to r. Of what? Of this function. But now on this real, this is the real axis, right? On the real axis, we said this angle is 0, theta equal to 0 here, remember? On the upper boundary, theta equal to 0. So z is simply r to the p minus 1, right? Theta is 0. I mean, z is r times e to the I theta. So, but on this line, on the upper line, theta is 0. So it's simply r. So that becomes r to the power of p minus 1 over r square plus 1 dr. Right? But then you have okay, this path. This path is from from infinity to 0, which is the same as I can change the orientation to make it minus 0 to infinity. Right? However, now the function is different because this is in the lower boundary, where z is r times e to the 2 pi I. Theta is 2 pi now. Okay. So I substitute that, it will give you r to the p minus 1 times e to the power of 2 pi I times p minus 1, right? Because theta is 2 pi now. Okay. This divided by z square plus 1. Okay, z square plus 1 is simply r square plus 1 again. I mean, you have to be careful about this only where you have some powers which are not integers. No, otherwise it doesn't matter. This part I just said. I mean, so I want to now look at this integral, this part of the integral. So in this part of the integral, z is what? Z is r times e to the 2 pi I, because theta is 2 pi, right? So just substitute that here. Right? So then you get r to the p minus 1 times this to the power of p minus 1, which is that, divided by z square plus 1. Z square plus 1 is r square e to the 4 pi I. E to the 4 pi I is simply 1, right, plus 1. So there is this. And then finally the last circle, gamma epsilon, integral over some, say, some small circle here. Okay. Now let's look at these integrals. I mean these two integrals. Gamma r integral. So here it's easy to see, I mean, how it behaves. This guy behaves like capital R to the p minus 1. This measure will give you capital R, right? I mean, the z on the gamma r is capital R times e to the I theta, right? So dz will give you r e to the I theta times I d theta. So but there will be one factor of r will come from there. So the numerator behaves like r to the power of p minus 1 plus 1, right? R to the p minus 1 comes from there and r comes from there. So basically r to the power of p. Whereas denominator goes like r square. Z is large, so I can forget about 1. So r square. So the whole thing behaves like r to the p minus 2. This whole integral goes like r to the p minus 2. But p is less than 2, remember. So this vanishes. In the limit r goes to infinity, that vanishes. Okay? I mean, this is the reason for this choice anyway, to begin with. So this integral vanishes. Okay? Now what about this integral? So here you have, so instead of r e to the I theta is epsilon e to the I theta, right, in the small circle of epsilon radius. But now epsilon is very small, so I can forget about that. It's only 1 dominates here. So you'll get here epsilon to the p minus 1 from there, and then epsilon from here, so plus 1. Okay, and this z squared is irrelevant because 1 is dominant. So this whole integral behaves like epsilon to the p, right? But p is greater than 0, strictly greater than 0. Okay, so in the epsilon goes to 0 limit, this vanishes. So this also vanishes. Okay, so then we are done essentially, right? Because this is the integral we are interested in calculating in the limit epsilon goes to 0 and r goes to infinity, right? This is that integral. This is also that integral up to a phase. This phase is constant, so I can take it out. So this whole thing, so that entire contour integral is equal to actually 1 minus e to the 2 pi I p minus 1, okay, times the integral that we are interested in computing. Right? So this is equal to, we are saying this here, this result. Yeah. So the conclusion is that this is equal to, let's say 2i I can take out, so 2i cancel, so there is this pi, pi times e to the I p minus 1 pi by 2 minus e to the 3 pi I p minus 1 by 2. Is that correct? Let me see. Yeah, probably should, must be, yeah. Did I make some mistake here? P minus 1? No. I mean, we can try to, yeah, so let's see what it is. I don't know this. So this is the same as if I take out e to the I pi p minus 1, okay, common factor. Okay. So this becomes e to the minus I pi p minus 1, and that becomes e to the I pi p minus 1. So I'm just trying to simplify. I don't know if I may have made some mistake here, some forgetting some phase, but let's see. So what is this? This is the same as minus 2i sine pi p minus 1, right? Because this divided by 2i is a sine of minus p minus 1, pi p minus 1. So this is minus 2i sine pi p minus 1 times e to the I pi p minus 1, right, times I. So that's the left hand side. Now what about the right hand side? This is equal to pi, and again let's take out e to the I pi p minus 1 from here. So you get here e to the I pi p minus 1, then the first term becomes e to the minus I p minus 1 pi by 2, right, I mean the first term, and the second term becomes minus e to the I pi p minus 1 by 2, which is again 2i times sine. So this is minus 2i pi e to the I pi p minus 1 times sine pi p minus 1 by 2. Okay, yeah, no, that, so it's okay, because I was worried about this this overall phase, yeah, but this overall phase cancels on both sides. I mean, sorry, yeah, this and that. So this is equal to that, we are saying, right? So okay. So from this, what cancels? So we are saying this is equal to that. This phase cancels. Minus 2i also cancels. Okay. So we are, what we have is then sine pi p minus 1 times the integral I is equal to pi times sine pi p minus 1 by 2, right? But then you know that sine of 2 theta is equal to 2 sine theta cosine theta, this trigonometric identity, right? So I can rewrite this as 2 sine pi p minus 1 by 2 times cosine pi p times p minus 1 by 2 times I, that's equal to pi sine pi p minus 1 by 2. So this sign cancels with that, and we are left with the answer I is equal to pi divided by 2 cosine pi p minus 1 by 2. Okay, which it should be the same as here. Yeah, here it is. Okay, this is the same as pi divided by 2 sine pi p by 2. This is because, again, use the trigonometric identity. What is it? Cosine of, first of all, this is the same as cosine pi p by 2 minus pi by 2, right? I just open this up down, which is the same as cosine of theta is equal to cosine of minus theta. Cosine is an even function. So this is the same as cosine of pi by 2 minus pi p by 2. Okay, I mean minus of that is that. But then cosine of pi by 2 minus theta is sine of theta, right? So this is called this theta. So this is the same as sine of pi p by 2. Okay, so that proves this. Okay, so this is the final answer. You see, it was quite. So the result of the integral is this here. It's, I mean, it's not easy to calculate that integral directly. I don't. In fact, again, I don't know of any way of calculating this. But you can check one thing. I mean, this has to be between 0 and 2. But in particular, let's take p equal to 1. Right? If I take p equal to 1, there is no branch cut. Okay. So actually, these steps cannot be done, cannot be used. Okay. Yeah. If p is equal to 1, you see, it's not, nothing is well defined in this entire steps. If you go through these steps, you see, for p equal to 1, this is 0. This is also 0, right? So 0 times I is equal to 0. But what we are doing in this process, you remember we divided this here. So 0 divided by 0. So it's not legal at what we are doing at p equal to 0. But at the end of the day, you see, this we obtained assuming that p is not 1. Okay, p is not an integer, but it is between 0 and 2. Okay. However, at the end of the day, I'm getting a result which is completely continuous. I mean, in this range, p between 0 and 2. So, in particular at p equal to 1 also it gives you some non-zero answer, it does not blow up. At p equal to 1 sin pi by 2 is simply 1. So, answer is simply pi by 2, right. But that you can check, because at p equal to 1 this is simply 1 divided by x square plus 1 dx is pi by 2. Remember that we did this. I mean, you can just change the variable x equal to tan theta and you immediately get that answer. So, even though p equal to 1 these steps are not correct, right, the final answer is coming out right. These steps are useful precisely for p not equal to 1, that is where this is useful, because there you cannot do this directly this integral. Say p was 1/2, let us say, you cannot do that integral. Okay. So, this is just an example of we will actually use this, I mean this result, please remember this result. Anyway, the notes are with you, that this integral is equal to that, because we will use that when we discuss gamma functions towards the end of this chapter. Okay. Any questions? Just out of curiosity, maybe try to do that in the second sheet and make sure that the answer is the same. So, take z equal to r e to the I theta, but theta is now between 2 pi and 4 pi. Things will change in several places. First of all, in this integral now, when you replace z by, so z will become r times e to the 2 I pi here, right. Here it will become z r times e to the 4 pi I, but also the poles, when you compute the residue, the poles will be z to the 5 I pi by 2 and 7 I pi by 2. So, if you do everything, put everything correctly, you should get the same answer at the end. One way to check, I mean, in fact, that is what where I started having doubt whether I missed some factors, is that this is a real integral, right. So, answer better be real, right. If in this various manipulations you see there are a lot of I factors, a lot of phases and so on floating around. So, if you have made some mistake, you might end up with an answer which is not real. That should tell you that you have made some mistake in the steps. Then you should go back and check the steps. Okay. So, now okay, if there are no questions, I will go on to analytic continuation. This is an important concept. Schwarz reflection. So, should we, is there any question on this? Sorry?
For the first integral, we used epsilon to r.
Yeah.
For the other, we used 0 to infinity.
No, sorry. This is, it is again minus r to minus epsilon. But I mean, because anyway, we are going to take r to infinity limit and epsilon to 0 limit. Yeah, true. This is from first integral epsilon to r, and the second integral is minus r to minus epsilon, to epsilon. Not minus r to epsilon, Yeah. This is the same r to epsilon. But yeah, in this case, anyway, we saw that the gamma r and gamma epsilon didn't contribute, became 0 in the limit r goes to infinity, epsilon goes to 0. So, finally, we want to take the limit r goes to infinity and epsilon goes to 0. So, yeah, true, yeah. I wrote infinity to 0, is it? Yeah, that's right. Okay. Anything else? No. So, okay, let's discuss this notion of analytic continuation. So, can I erase all this now? 3:15. No. I'm wondering whether I should do that or something which will take less time. Okay, let's do this. It's not, won't take much time. So the first thing that okay, there's first we try to prove a theorem. We prove a theorem. The theorem is the following: if let's suppose you have in some region, in some region, let's say okay, here somehow D is used for region, doesn't matter. So D is a region. Okay, so so suppose f1 and f2, these are two functions defined in this region D, and they are analytic. Okay. So these two functions are, so there is some region D, let's say, and inside this D, these two functions are analytic. F1 and F2 are analytic inside here. Okay. And furthermore, so there are several statements one makes. So suppose I have Z is a point, some point here. Okay, Z naught, let's say some point, and and suppose that this happens, that these two functions are equal in some region, in some neighborhood of Z naught. Okay, so suppose f1 of Z is equal to f2 of Z in some neighborhood of some point Z naught, of Z naught. Okay, then this or either this or say, or there, suppose there is some segment, some small segment of some curve inside. Let's call it some C. Suppose f1z is equal to f2z on C. Okay. So whenever z is a point on the C on this curve, these two functions are equal. Okay. Or even more general than this, suppose f1, suppose there is a sequence of points z1, z2, zn. This is an infinite sequence of points which has an accumulation point, which has a limit point or an accumulation point, the same thing, which is a limit point, let's say z prime, let's say some limit point z prime, okay, and f1 of z, all of these zi's is equal to f2 of zi for all of this all the points of the sequence. So how to picture it? So there's there's a sequence of points which has an accumulation, which accumulates at some z prime. Limit, there's a limit of the sequence. It's in that sense. Okay. I mean, accumulation point. You remember this definition of accumulation point, right? Okay. If any of these things happen, then the statement is that then that would imply that f1 of z is equal to f2z everywhere in D. It's a very powerful statement. Very, very powerful statement. Actually, it's sufficient to prove this, right? Because these two are just a consequence of that. Because, I mean, on a curve C, of course, you can consider infinite number of sequences which have accumulation point, right? So if this is true, then obviously this is also true. And similarly, also this is true, because in any neighborhood, again, there are infinite number of points which are accumulation points, right? So the most powerful statement is this. So how do you prove that? The proof is the following. You remember when we discussed the zeros of the, the zeros of an analytic function. You remember, I don't know if you remember that, because I said it in a just passing, very quick remark, that the zeros are always isolated, right? You cannot have accumulation point. And the reason for that, I just remind you, because maybe you have forgotten about it. I mean, if you take, suppose there is some nth order 0 at some point z naught, let's say, because I use z naught here, I don't know, at nth order at z equal to say some u, u is some complex number, zu. In that case, you know, what does it mean? The Taylor expansion, the definition of this nth order 0 was that the Taylor expansion will start from z minus u to the power of n, right? And that coefficient which appears here, a n, is not 0. Okay? Because if it was 0, then the next term would be z minus u to the power of n plus 1. Okay? If this was 0, then you would say that it is a n plus 1th order, not nth order. Okay? So this is so this means that the Taylor, so what does it mean? Taylor expansion starts from here, starts at z minus u to the n, and the coefficient a n is not equal to 0. Right? Of course, it could also happen that in fact everything is 0, right? I mean, then it is trivial. If everything is 0, it's a trivial function. It's just a 0 in the entire domain of analyticity, right? Where this Taylor expansion works, right? It will be 0 identically. So you have to prove nothing. So, but we'll assume that something non-trivial. It's not identically 0. So in that case, it will be this n will be some finite number, right? So whatever the n is, then you have this that coefficient is not equal to 0. But if the coefficient is not equal to 0, then if I point u here and look at some neighborhood of point u, if that coefficient is not 0, then I mean so you see this function, if you go to some small, nearby point from u, okay, then I mean this is still dominant compared to that, right? I mean z minus u to the n plus 1 is still small compared to z minus u to the n, because it's very near. Z minus u is very small. Okay. So the moment z is in some neighborhood of u, so z is not exactly equal to u, then this is not 0, right? And a n more generally, in fact, let me write it like this. So so what this means is the following, that the function can be written as z minus u to the n times some another analytic function h of z, this, and the statement that a n is not 0 is a statement that h of u is not equal to 0. H evaluated at u is not equal, because I can take out z minus u to the n as a common factor out, right? And whatever is remaining, that in infinite sum, right, that I just call it as h of z. So the statement that a n is not 0 is the same as statement that h of u is not 0. Okay. Now if if you go to some small neighborhood, but some other point, not z equal to u, then this factor is certainly not 0, right? I mean, this is not 0. If z is not equal to u, this is not 0, right? Now h of z, I mean h evaluated at u is not equal to 0, right? So because it's a continuous function, the analytic functions are continuous, in some small neighborhoods h will not become 0 suddenly, right? The continuous function, I mean, you start with something non-zero, the very next point it cannot become suddenly 0, right? So there will be some small neighborhood where this h will not be 0, which means this function as a whole, this is a total function is that that function will not be 0 in some small neighborhood of u, right? So that means 0 cannot have an accumulation point, right? That's the statement. If there was an accumulation point, that would mean that in any neighborhood of u there is another 0 there, right? That's a statement. So zeros do not have accumulation point. Okay. But now if we are saying, to consider this case, f1 of zi is equal to f2 of zi, then that means if you take the difference, call this function f is equal to f1 minus f2. Then this function f has zeros at the points, this sequence which has an accumulation point. That's a contradiction, right? The only possibility is that then that function is identically 0, which could have been the case, right? If all the terms were 0 in the Taylor expansion, then of course it will be 0, right? It will be identically 0, right? So this is the only possibility. So if this happens, then the only possibility is this function f is identically 0. Right? But that means f1 is identically equal to f2 in this entire region where they are analytic. It's a very strong statement actually, this, if you think about it. I mean, I mean, we already knew somehow to some extent, right? Because remember the integral representation for the analytic functions. Integral representation was Cauchy integral representation, that if you give me the value of this function on some curve, closed curve, then I can determine the value of function anywhere inside by using the Cauchy integral formula, right? So that we already, so and uniquely, right? I mean, once you give me these values here, uniquely tells me what is the value down somewhere inside, right? But actually it's much more powerful than that. We are saying essentially that if you give me the value of function even in some small segment, right, then it uniquely fixes the function everywhere, right? Or even more generally, just at a sequence of points which have an accumulation point, if you specify the function there, it's uniquely fixed. Now, so what is the meaning of this? I mean, how one can use this actually? It means the following. Now I come back to analytic continuation. Okay, so the idea is, suppose, so I go to analytic continuation. Now suppose I am given some analytic function f of z in some region, and let's suppose I'm given another analytic function, say let's call it f1 of z here, and another analytic function f2 of z, which is analytic in this region. But I don't know, I mean, this function I cannot extend, I mean, I don't know, this function is defined only here. I don't know what is the definition. It's just defined in this region. As an example, you remember this geometric series 1 plus z square and so on. This is only defined for z less than 1, right? It's only defined there. And there, of course, in this region, I know it's 1 over 1 minus z. Right? I mean, so, okay. I mean, we were just lucky that we knew what this was. In general, if you give me a series, I wouldn't be able to write down, you know, some neat formula like that. No? Okay, so in general, I have some maybe some series here, but I don't know really what that actual value. I mean, it's convergent and so on. I know, but I know that this series is not defined beyond some region, right? But here I may have another series, right, which is only defined in this region, right? But in the overlap region, suppose it happened that f1 was equal to f2 in the overlap region. Okay, then you say that f2 is an analytic continuation of f1 to that region. Okay, so if it happened that in the overlap region, let's call it this region is R1, that region is R2. In the overlap region, R1 intersection R2. So if in R1 intersection R2, f1z is equal to f2z, then you say that f2 is an analytic continuation of f1 to this region, or vice versa, f1 is an analytic continuation of f2 in this region. So that's then you say that f2 is the analytic continuation of f1 to region R2. This of course would be a meaningless statement if this continuation was not unique, right. Suppose there was another function f3 here, which also had satisfied the property that f3 was equal to f1 in this region, right. But if f3 was different from f2 out here, then it's not a very meaningful concept, right. Then it would say there is not a unique analytic continuation. But that is not the case, because we have already proven this theorem. So you see, if there was an f3 which also coincided with f1 in this region, that means f3 and f2 are equal in this region. Therefore, f3 and f2 must be equal everywhere, right. So it's unique. This is why it's so useful. This concept otherwise would be meaningless, right. So this way you can keep, and now maybe there is another, I mean this region is only up to this point, but then maybe there is another region where there is f3, which again in the overlap region f2 is equal to f3, you know, then this will be analytic continuation of f2, and therefore analytic continuation of f1, you know. So this way you start mapping out the as much as you can, you know. Of course there will be some places where you cannot, well, I mean there will be poles in general, no. So okay, there that's what it is, poles will be there, or even branch cuts, you know, multivaluedness. So this way you can keep extending. So this way of doing it, you will arrive at you will just cover one sheet, right. But when you branch cut, whatever the branch cut you choose, there you will get stuck. Well, you can then try to analytically continue, you will automatically go to the second sheet. So this way of analytic continuation, you will automatically go through this branch covering. Okay. I mean, just to take one example of this again, this harmonic thing. You see, actually this example is given here. I mean, roughly the picture, the reason for this thing is following. So I mean, you see that here in this geometric series. So here is my origin. 1 is here, and you had this. I mean, this circle of radius 1, right? Where this sorry, this circle doesn't look like a circle here. Yeah, where this is well defined. This series makes sense, right? So inside this circle, it makes sense. However, really and of course here this geometric series, let's call it f1 of z. This is equal to 1 plus z square, etc. Okay. In this region, it's simply 1 over 1 minus z, where it is defined. Huh? Now this is actually pole only there, right? Not everywhere here. However, this series doesn't make sense even here. I mean, under this point. Or beyond it doesn't make sense. Huh? However, there's nothing wrong with this function. This function is perfectly okay everywhere. Only here there is a pole. At that one point there is a pole. So I mean, you could analytically continue in everywhere, and analytic continuation of this geometric series will be simply 1 over 1 minus z, which is everywhere okay except at a pole at z equal to 1 by this argument. Or yet, I mean, even okay, this is immediately obvious, but take another case where I mean the same. Yeah, so let's say z plus half. So in fact, it is given here, this example. So consider this series now, f2 of z, which is 2/3 plus 2/3 square times z plus half, yeah, z plus half square, z plus half plus, so actually let me write it like this. So 2/3 is a common factor, 1 plus 2/3 z plus half plus square of that, so 2/3 z plus half square, and so on. So this thing, so 1 plus this plus square of that plus cube of that, and so on. So it's again a geometric series, but the argument is, the variable is this. So this series is convergent so long as 2/3 z plus half modulus is less than 1, right? this is convergent because it's geometric series just with that variable. That means this is series convergent when, so long as z plus half modulus is less than 3 half, right? So now what is the picture of that? Z plus half, so that is this is a circle at around minus half. So if this is minus half, right? So you take a circle of radius 3 half. So once again you see its limiting point is again the pole position. But this is a circle of this size, you see, much bigger than that, the previous one. I mean, this F1 was defined in this small circle, unit circle. F2 is well defined on a circle whose center is not 0 but minus half and the radius 3 half. So it's the bigger region. And in these two, of course, if you evaluate this, what is this object? I mean, let's compute that. The result, of course, is simply, so F2z, I mean, in this region, you can sum this series, and it's simply, okay, 2/3 is a constant here, 1 divided by 1 plus this object, right? 2/3 times z plus half, right? That's what it is. It's geometric series. And what is this? Let's simplify that. Take out the 3 factor as a common factor. Actually, take out 2/3 as a common factor outside. So this becomes, and that 2/3 will cancel with that, right? So this is the same as 1 plus, no, I should do, sorry. No, so it should be minus. Is it minus? Yeah, I should put a minus here. Huh? No, sorry, it's minus. This is minus here, correct. This is minus. 1 over 1 minus z. Yeah, this geometric series is 1 over 1 minus z. Whatever that is, it's 1 over 1 minus that. So you get here 3 half minus z plus half, right? This is the same. Just take out 2/3. So here it becomes 3 half, and that 2/3 will cancel with this 2/3. Okay. So you get here 1 divided by 3 half minus z plus half, which is the same as 1 divided by 1 minus z. 3 half minus half cancels, right? So it actually is the same function. I mean, we deliberately chose, I mean, in this book is deliberately chosen to be the same function. But you see, they have very different functional forms. If you just look at the series, you cannot immediately just say that this is the same function eventually, right? And besides, the radius of convergence is different. The region of convergence is different. One is defined here, other is defined there, right? But they are the same. So you can even say that F2 is an analytic continuation of F1 to this region. So this is the way you, yeah. This is in general possible. I mean, you know, okay, here I just gave some simple examples, you know, which are known to you, the geometric series. But in general, even situations where you do not have any neat form for the sum of the series, right? Still, you can go through this procedure of analytically continuing. Okay. Okay, I will maybe today if I start doing Schwarz reflection principle, it will take longer time. So let me just do one thing. No, maybe I should stop. I mean, I remember I mentioned to you one thing, that nth, if you have a polynomial of nth in the first chapter, if you have a polynomial, you remember the characteristic polynomial. If you have a determinant of n by n determinant, and then when you look at the determinant of that matrix minus lambda times identity, where lambda is supposed to be the roots of that is eigenvalues, right? So if you take this, it will become an nth degree polynomial in lambda. And I told you that there are n roots in general complex roots. Now, of course, this you all know. I mean, in the sense that, but probably without seeing the proof of that statement. You know, you can actually prove now using this residue theorem again. Okay. So let me just. Yeah, go through that, because that I can do probably in 10-15 minutes maybe. Okay. Yeah. So first I need to prove a theorem which is the following statement, that suppose f of fz is a meromorphic function. Remember the definition of meromorphic is basically it's analytic functions except at some isolated points where it has some finite degree pole, nth degree poles, where n is some finite number. So meromorphic function with, so in some region, everything is in some region R, and let's suppose this f has zeros. Let's say how many, let's call it z. Okay, so this is my region R, and I choose some contour C. So the region is R, so the whole blackboard says region, and I choose some contour C, which is inside the region, of course. So I close contour like that, and let's suppose this f has z zeros inside this contour, inside C. So inside here. I mean on this, okay. And so I choose the C in such a way that f has no zero on the C itself, but inside the C it has, say, z zeros. Okay. And at some positions, let's say at positions z1, z2, no, z, not z. This is not a very good notation. Okay, so z zeros total inside the C at some positions zi, I equal to 1 up to z, of course, of order, order of the 0, right? At each, the order of the 0 being, let's see, ni. So what is the meaning? So if there is a z1, z2, etc. Okay. At z1, this function has a 0 of order n1. N1 means it has a, the order of the 0, you remember? that the first up to first n minus 1 derivatives vanish. Function and the first n minus 1 derivatives vanish. And then nth derivative does not vanish, which means the Taylor expansion will start at that power, z minus, this means that if you do Taylor expansion, it will start with z minus zi to the power of ni, the starting. And this coefficient is not 0. So that's what it means, ni. Okay. And let's see, has how many poles? And has p poles, let's say, at, let me use ai. At positions ai, I just use the same symbols. So at z equal to ai, at z equal to bi, let's say, where bj, j goes from 1 up to p. Okay. So these are a1, a2, etc. And similarly, some points b1, b2, etc., where it has poles of order. Let's call it mj. So do you remember again the order of the pole? That is the worst singularity. That's what it means, right? In the Taylor expansion, it will start. So this Laurent expansion. This means the Laurent expansion will start. The worst singularity will be 1 over z minus bj to the power of mj. That will be the worst singularity. You won't have more negative powers. That's the worst power, and then less worst powers. Okay, that you remember this definition, the order of the pole, and this you should remember always: order of 0 and order of pole. Okay, so this is given. Okay, then the theorem says the following. Okay, also let's do the following, and also further, let's suppose a function g is given. Okay, and so this is all about f, and let's say g is another analytic function again. is an analytic function. It has no poles anywhere inside. It may have zeros and so on, but it has no poles. Analytic function in R. Okay. Then the integral 1 over 2 pi I around the contour, this is a closed contour, g of z, and then df by dz divided by f, okay, dz. So this is in this contour. So you see, I mean, as I told you, I'm choosing the contour such that f has no zero or pole on C. That is because I have 1 over f here. Okay. So if it has a 0, there will be problem. Right. Similarly, if it has a pole, also there will be problem. Okay. We will see that. Okay. And this is equal to, the statement is this is equal to sum I equal to 1 to z n I g a I minus sum j equal to 1 to p mj g bj. So the meaning is, so the result of this integral is a sum of the at these zeros, right? So here remember the order of the 0 was n1, this is n2, etc. Here the order of the pole is m1, m2, etc. So what you do, you multiply by the order of the 0 at the point a1 and multiply that to g evaluated at that point, right? And then sum up over the zeros, right? And then subtract, there's a minus sign for all the poles, but subtract the same thing. So order of the pole times the g evaluated at those points. Okay. So that is the result of that integral. I mean, that is the theorem. So, but the proof of that's very straightforward actually. It's completely straightforward. It's simply the following statement that I mean, where are the possible poles for this guy? So let's see. In the place where f, I mean, where f is not 0, this is certainly denominator is certainly finite. I mean, when f is not 0, 1 over f has no divergence, and the df over dz will be also finite. I mean, any place, any plane, regular point, which is not 0 or infinity, df by dz will be well defined because its function is analytic there, right? Df or dz will be finite. F will be also not 0 in other points. So this ratio will be finite everywhere else. Okay. The only possible problem would be at the poles and the zeros. Why zeros? Because I'm dividing by f, so I have to also worry about the zeros of f. So this is the only region where it can have any problem. So I can deform this contour and write it and consider small contours around these points. The result is the same, right? By Cauchy theorem. I mean, the result of this contour integral is the same as the sum of these contour integrals around the zeros and poles, because nowhere else there is no problem. Everywhere else this integrand is completely analytic, right? So by Cauchy theorem you can deform this contour here. So let's just focus on individual ones. So let's say, for example, on A1, let's focus at A1. What happens around A1? So we said function f, so near A1, since it has an one-th order of 0, f goes like z minus A1 to the power of n1, right? Or in general, let's say ai, it will be z minus ai to the power of ni with some coefficient ci, let's say, some coefficient, and then okay, higher order terms, right? But the ci is not 0. Important point is ci is not 0. Okay. So how will the df by dz go like? Df by dz, just start taking differential. So you'll pick up an ni from there, times ci of course, and z minus ai to the power of ni minus 1 plus higher order terms. Higher order terms in the sense that, I mean, this is the leading term when z approaches ai, because our next one will be ni plus 1 power. So that will be even smaller than that. No? So similarly here, the next one will be smaller than that. So when I take the ratio, this divided by this, what I will get is, I mean, so this divided by that. So it will start off, so df by dz divided by f will start off as, you see the ci cancels, ni power, here is ni minus 1. So there is a 1 over z minus ai, and then times ni. It will start off as this, okay, plus something which is analytic. Okay. I think, is that, you can just make an expansion. I mean, both sides you can, this was only the one term, right? If you keep the other terms, there will be an expansion, but expansion will have some higher power, positive powers of z minus ai. So that will kill this pole, and everything else will be finite. Okay. I mean, you can just try to work out. I mean, just keep the next term, both terms, and take it, divide, and then make an expansion. So this will be the leading pole, Laurent expansion of this guy. So this will be the pole, and other will be all without any singularity. Okay, so near ai. So then I can just use the residue theorem, right? So I evaluate this. So what I have to do is a first order pole. So I just multiply this quantity g times this thing. So I have to actually multiply by g also, right? So this is g, that g is there. So now I have to take the residue. So I just multiply by z minus ai and evaluate this at z equal to ai. So you get ni times g evaluated at ai. So that's this point. There is a 2 pi I, but that I am dividing by 2 pi I, so that cancels. 2 pi I times the residue, that cancels. So for the zeros, you see that. For the poles also is the same situation. So now let's look at the near bj. Okay, so we are saying it has a mth order pole. So near z equal to bj, it goes like 1 over z minus bj to the power of mj with some coefficient cj which is not 0, right? And then less worse powers. So in other words, if I had taken this out as a common factor, it will go like cj plus z minus plus something else, some cj plus I know cj1 z minus bj, etc. Right? Because this is the worst power, I can take this out, and then after that is a regular expansion. Now let's look at the df by dz. So it will go like, so the first term, when I apply the derivative, it will give me minus mj, because this is negative power, right? The negative power. So it will give you minus mj times z minus bj to the mj plus 1 times cj, and again less worse powers. So once again you can write it as this plus something else, I don't know, c tilde 1j z minus bj, etc. I mean, you can write like that. Now take the ratio of the two, and this time you find, okay, g is still there, g I keep as it is. Ratio this divided by that, you see the mj power cancels, but there is still one left over. Cj also cancels, right? And then there is simply minus mj. So this is minus mj times z minus bj, 1 over z minus bj, plus regular terms. So once again, the pole is only there. So first order pole. So multiply by z minus bj and evaluate it z equal to bj. So you get that mj and with a minus sign. And that minus sign came because when I took the derivative, there's a minus here. Right? So this is the difference between 0 and good. So once you accept this theorem, then I'm ready to prove that's called the fundamental theorem of algebra, that nth order polynomial has n zeros. Okay, it's called the fundamental theorem. So consider a polynomial, nth degree polynomial, which is of the type z to the n plus. Let me see. Yeah, okay, I can always make this 1 plus a n minus 1 z to the n minus 1. A n minus 2 z to the n minus 2, etc., all the way up to a0 plus a0. So, this is a general nth order polynomial, right. Now, the theorem is that this can always be written as, so this can always be expressed as z minus say zi to the power of some ni product I going from 1 to some say z, not z, let me not use this capital I equal to 1 to, okay, here they, I do not know why they, I think they just use z here because z stands for 0, no, that is why, but do not confuse, let me not use that, some p let us say, I equal to 1 to p, this can, I can always write it in this way, that is the theorem, okay, where sum over ni I going from 1 to p is equal to small n, I mean the n, whatever the nth polynomial, this n. Okay. So, that gives you basically all the roots, no? Some root, I mean of course, ni just tells you that the zi appears n times, right, this is a degenerate root and n times, but you are finding all the roots. So, this is a theorem. How do you prove that? So, the proof is the following. Let us carry out this integral of just use the previous theorem, this theorem, and take this dpn over dz divided by pn z, and g, for the function g I just take 1, after all g was any analytic, 1 is an analytic function anyway. So, I take g equal to 1 and I choose a contour where the contour is a large circle. Okay. Notice that, so the following thing, that whatever the position, I mean look at where this can vanish. This has certainly no pole, it is an entire function, so there is no pole, only thing that can happen is you can have zeros, right. But where can the zeros be? Surely the zeros must be in some finite region, I mean it is not, because as z goes to infinity, you see this dominates compared to all the other things, right. So, for large z this dominates and certainly it is not a 0, right. So, zeros can only be in some finite region, right, cannot be far, very very far away, okay, not infinitely far away. So, I can always take a circle, right, which it contains all the possible zeros of this function, this polynomial, right. I mean that would not have been possible if zeros was going all the way to infinity, right. But that is not the case here, because as z becomes large, actually this function instead of becoming 0 is going to infinity, right, because this dominates, those things are negligible for large z. Okay. So, the first statement is that the zeros of Pn are in some finite region because as z goes to 0 infinity, Pn behaves like z to the n, which actually goes to infinity. So, there is no 0 very far away. So, all the things are in there. So, choose the C. So, we choose the C so that it, so C is a, let us say some circle, let us take gamma r is a closed circle, choose gamma r so that all the zeros of Pn are inside gamma r. Okay. Then okay, so then what? Okay, so what this theorem is saying? Apply the previous theorem. That is, this is simply equal to sum over ni, I equal to 1 to z, right? Where p, I call it p now, I equal to 1 to p. So these are the so whatever the positions are. We do not know. Okay, wherever it is 0, wherever this is 0. Let us say at zi this is 0. Okay, then I mean. And look at, so it is just going to count what is the order of the 0, ni is the order of the 0, and you just sum it up. That's the result of that from the previous theorem, right? But now what we want to show is that actually this quantity is equal to n. This is what we want to show. because if you hadn't shown that, of course, then this is obviously true, because if zi's are the positions of the pole with ni thing, then I should be able to always write factor out the z minus zi. No? So this part is trivial. The part to prove is this one. Okay. So how can we prove that? Well, let's do a direct integral. We can also do a direct integral for take a very large circle, right? Large radius. So in the large, when z is very, very large, so radius, so z is r times e to the I theta on gamma r, I can choose that. And then so when r is large, Pn we said is just z to the n for large z, right? So this is r to the n e to the I n theta, right? And what is dPn over dzn? Dz, that is simply just take the derivative n z to the n minus 1 for large r, right? Which is n times r to the n minus 1 e to the I n minus 1 theta. Okay. And finally, dz, of course, is as usual I r e to the I theta d theta. So put them all together. So this the left hand side is simply the integral. I mean, there is a dz here. Integral, so I r e to the I theta d theta, that's a dz. This in this ratio, you see this divided by that. So r to the n minus 1 removes n minus 1 powers, but there is 1 power left over. So there is a 1 over r here, and there is n here. So n comes in the numerator, and e to the I n minus 1 theta, this is e to the I n theta. So what is left over when you take this divided by that is e to the I theta here. So now r this cancels. You have here, and sorry, let me put it. So this was one. There's a 1 over 2 pi I here in that theorem. 1 over 2 pi I. So 1 over 2 pi I, and 0 to 2 pi integral. So I cancels with that. The integral is simply d theta. So that's just 2 pi. 2 pi also cancels. So the result is n. You're okay. Okay. Now I finish now. Okay. So that's the final statement here. It's, okay. Okay. So I think, yeah, maybe I should make a move now. We'll discuss. I mean, if you have any questions, we can discuss it on Tuesday, next Tuesday.